All right, we are recording. So we are looking at section 11.7, maximum and minimum values. You will not have any formal homework on this section, but the MATLAB assignment number 5 has a problem based on this section. And so I want to talk about this section a little bit with you. So up to now, you have not needed to find any maximum or minimum values of a surface. Okay, and but yet in calculus 1 and 2, you dealt with maxima and minimum values of functions of one variable. Well, if you have, for instance, and we'll keep it kind of simple here, if you have a function of two variables, which would be a surface, there in figure 1, you see local maxima and minima, and then you see an absolute maximum, absolute minimum. And this is what we are trying to determine in section 11.7. What conditions would we need to find to find maxima and minima? Well, in calculus 1, when you had a function of x, to find the maxima or minima, what did you do? You took that derivative function and set it equal to 0, and then you solved to get your x values. Well, the problem is a little more complicated in when you have a function of two variables, but the idea is still the same. So if you think about if you look at, for instance, the absolute maximum there, okay, the absolute maximum. So at the very top of that hill in figure 1, it's flat. So if you were to take a tangent line with respect to the direction of the x-axis and another tangent line that points in the direction of the y-axis, those tangent lines would have slopes of 0. They would have to, right? So in that case, because tangent lines for an absolute for a maxima or a minima, well, if you look at like the absolute minimum there, if you think about the bottom of that valley, it's flat at the very bottom. So any tangent line where the minimum is would have to be horizontal, and so tangent lines pointing in the x direction and in the y direction would have to have slopes of 0 in those directions. So based on that, there's a theorem called Fermat's theorem that says, okay, well, to locate the maximum or minimum, just take the partial derivatives of the function with respect to x and y and set them equal to 0. And then you can, based on those two equations, hopefully you can find what the maxima or minima are. So and essentially, well, you have to find the critical points, right? So to find before you determine whether you have a maxima or minima, you have to find the critical points. So in calculus 1, to find the critical points, you took the first derivative of the function and set it equal to 0, and then you'd solve for x, and that would give you your critical points. How many remember that? How many remember that calculus 1 doing that? It's been a while, but you remember doing that? Okay, Mary remembers that, sure. And Christopher and Angela, sure, absolutely. So we do the same thing, same idea here. It's just we're going to have two partial derivatives set equal to 0, and then that gives us a set of two equations, and then we can solve for two variables, x and y, because now the critical values or the critical points are going to occur for coordinates x and y. Right? And so if we look at an example here, okay, like example 3, they want you to classify critical points. So they wanted you to find local maximum, minimum, and saddle points of this function. Now, you know, what's a saddle point? A saddle point would be, I mean, I think we know what a maximum value is and a minimum value is, but what would a saddle point be? Saddle point would be a situation like you see here in figure 3. So in figure 3, you have, if you look at that saddle, with respect to the x-axis, it looks like the bottom there in the bottom part of the saddle, where, like, say a person sits, okay, with respect to the x-axis, that point looks to be a minimum, or a maximum, I should say. But if you look with respect to the y direction, the y-axis, that point appears to be a minimum. So we call that a saddle point when in that situation. Well, in that situation, if we want to be able to identify saddle points, maxima, and minima. But first, we have to identify the critical points. So again, we're going to use the Fermat's theorem here. We're going to use Fermat's theorem and take the partial derivatives with respect to x and y, set them equal to 0, and then solve for x and y to get the critical points. And the book has a very nice little example, okay, this example 3. So here you have a function f of xy equals x to the 4th plus y to the 4th minus 4 times x times y plus 1. Okay, and all right, what do we do? First, we have to locate the critical points. So you take the partial derivatives with respect to x and y. Okay, you take those, and I don't think it's too hard to see that those are your partial derivatives. And then what you have to do is you have to set those partial derivatives. Okay, let me just highlight here. You take those partial derivatives and set them equal to 0. And you see what you have then is you have two equations with two unknown variables, and that allows you to solve for x and y. So how would we set this up? Well, let me go to the whiteboard here, and I am recording this. Let's go to the whiteboard. So the way this works, so this is, we're looking at example 3. So the way this works, let me just write down what we had. We had partial derivative of f with respect to x equals 4x cubed minus 4y, and we set that equal to 0. And then we had the partial derivative of f with respect to y. That was equal to 4y cubed minus 4x, and we set that equal to 0. Again, this is example 3 from section 11.7. Okay, so this then gives us, then if we divide through by 4, we'll have x cubed minus y equals 0. And this second equation, if we would divide through by 4, we get y cubed minus x equals 0. Now what we can do is we can say, okay, this first equation, if x cubed minus y equals 0, that means x cubed equals y. So we can take x cubed equals y, and we can substitute that in for the y on the second equation. Okay, so the second equation, right, is y cubed minus x equals 0. But now that's going to be x cubed minus x equals 0. Or x to the 9th minus x equals 0. Okay, so if we have then 0, let's try to solve for x. If we have 0 equals x to the 9th minus x, we can factor an x out, and that's going to give us x times x to the 8th minus 1. But x to the 8th minus 1 that can be factored as x to the fourth minus 1 times x to the fourth plus 1, right? But x to the fourth minus 1 can be written as x squared minus 1 times x squared plus 1. So we were relying on our factoring skills here. But then we can even go a step further. We can even go a step further because x squared minus 1, that factors also. So we end up getting then here, okay, and again, this is example 3 that we're looking at from section 11.7. We end up getting 0 equals x times x minus 1 times x plus 1, okay, times x squared plus 1. Hold on here. I got to be careful. One moment here. Yeah, times x squared plus 1 times x to the fourth plus 1. Are there any questions on that? Okay. Well, so the roots or the zeros of the function, okay, are going to come from these three factors: x, x minus 1, and x plus 1. Okay. The other two factors, x squared plus 1 and x to the fourth plus 1, those have complex roots. They don't have real roots. How many remember complex roots? Maybe back in pre-calculus, you had to find real roots and complex roots of polynomial equations. That's what we're doing here. So x equals 0, x equals 1, and x equals negative 1. Those are the roots. Those are the roots of our equation. And now that we know those x values, we can find the y values that go with them. Okay, so so far so good. All right, so let me go back to the problem then. All right, so again, here's what I showed you in on the whiteboard, is solving this equation, and then the three real roots, which are the ones we're interested in. X is 0, 1, negative 1. And if we substitute in 0, 1, and negative 1, if we put in x equals 0 in the function, and the function, remember, was x to the fourth plus y to the fourth minus 4 times x, y plus 1, we would get a corresponding value of hold on here, corresponding value of 0. Let me show you that on the whiteboard. So let me just show you that. So let's see here. Let me go ahead and remove this. So, okay, so when x equals 0, okay, hold on. Hold on, I'm not saying this right. So we had x equals 0, x equals 1, and x equals negative 1. So, one moment here. One moment, class. So remember, one of the equations we had was x cubed minus y equals 0. Well, if x equals 0, then 0 cubed minus y equals 0, y equals 0. So that means, so I'm doing this now for x equals 0. Maybe I'll try to kind of separate this out. So when x equals 0, y equals 0. And so one of the critical points, okay, let me just make sure I'm using my term. Yeah, this is one of the critical points, 0, 0. Now when x equals 1, again, because one of the equations we had was x cubed minus y equals 0, well, 1 cubed minus y equals 0. So 1 minus y equals 0. So 1 equals y. And so 1, 1 is another critical value. Another critical value is 1, 1. And when x equals 1, I won't go through the steps there, but for x equals 1, negative 1, 1 would be the critical value. Okay, let me just check one thing here. Yes. So these are your critical values. And they determine then where there are maxima or minima on the function. So if we go back to the problem itself, we go back to here is a picture of this function. And you can see it has three critical values because there are two minima. Okay, in this parapant surface, there's two minima and there's one maxima. Okay, two minima and, well, I want to be a little bit careful here. So like graphically at the origin, there's actually, well, no, let's do, so 1, 1, 1, okay, if you think where x is 1, y is 1, that's going to correspond to that right, that valley on the right in figure 4. When x is 1, y equals 1, the surface clearly has a minimum. And when x equals negative 1 and y equals negative 1, that's back in the third quadrant. That's going to be that left minima there. Okay, so, but at the origin, there's going to be a saddle point because we don't, it's not a maximum or a minimum. It's not, there's no hill at the origin. It's a saddle point. But now, how do we actually know what the how do we like mathematically determine then where minima, maxima, and saddle points are? I mean, graphically we can see for our three critical points which correspond to minima, and in this case, saddle point and two minima. But how do we mathematically determine that? Well, there is a theorem called the second derivatives test. And this is gone through also in some detail in MATLAB assignment number 5. The proof is in the back of the book, but there is a D, we call it a D function. First of all, we have to be sure, I will just mention this. We highlight that and make this like that. One moment. So first of all, hold on, I didn't highlight everything. So first of all, we have to find the critical points, and that's when we set those first derivatives equal to 0. And then after we do that, we utilize this D function, which is defined as you see it. And based on A, B, and C below, that determines whether you have where the critical point indicates a minima, a maxima, or a saddle point, which would be not a local maxima or a minima. So the part A there, when d is greater than 0, and the second partial derivative with respect to x is greater than 0 at the critical point, then the function has a maximum there, or a minimum there, I should say. And that actually makes sense, because when a second derivative with respect to x is greater than 0, there's concave up located at the critical point, and that means you have to have a minimum there. Part B says if d is greater than 0 and the second partial derivative with respect to x is less than 0, then the function is a local maximum. And that makes sense, because if a second partial derivative with respect to x is less than 0, you have concave downness at that critical point. And so that critical point would indicate a maxima. And then part C says if d is less than 0, the function's not a maxima or a minima. So it would be a saddle point. So what they do in this problem then is they go forth. I showed you the part where they found the critical points, but then they go through and compute the second partial derivatives and the value of d, and then they evaluate all the second partial. Well, I want to be careful here. I might have said no. Yeah. So to compute the value d, the function d, you need the second partial derivatives with respect to x and y, and then the mixed partial derivative. Okay. So they get the value of d there. They get the function and then they just substitute in the critical values into the function d and into the second partial derivative with respect to x. And that's how they determine that at 1, 1, you have a local minimum, and at -1, -1, you have a local minimum, and then at 0, 0, since the d value is equal to -16, at the origin, that surface has a saddle point. And that's how you use this second derivatives test. Okay, and it's also outlined in MATLAB assignment number 5, but I just thought we should go through with it just so you could see it with a particular example here. Are there any questions at all? Okay, all right. So this approach, this second derivatives test approach, it's to where we find maxima and minima or saddle points. I mean, the whole process in section 11.7 it's a beautiful process, but I caution you that it works well when you have where things work out beautifully, like this example 3. Everything worked out beautifully because you were able to factor things. Okay, you were able to like this part here, you were able to really you were able to find the critical points, and everything factored nicely. And so it's a wonderful, beautiful approach if you have a problem that can be worked out nicely. But a lot of times in mathematics, and I've seen this in my own experience in graduate school, you'll have functions of several variables that you need to maximize or minimize, and you can't really use the second derivatives test easily. So there are algorithms that can locate maxima, that can find critical points and locate maxima and minima. There are programs that are like nonlinear maximization or minimization programs that are usually available in with software, with different types of languages, I'm sure MATLAB has one available. I'm sure like R, I don't know if any of you use like S plus or R. That's usually a statistical language, but that has a nonlinear maximization as well program. So this is a nice technique to help you intuitively understand how maxima or minima can be found. But in many situations, you have to use what's the word I'm looking for? Numerically find where like your critical points are and where the maxima or minima are. Okay, so on that note, I will stop the recording, and you have enough now to be able to understand the second derivatives test for MATLAB assignment number 5. Okay, great. I will stop the recording.